Okay, so now we can start chapter 7, since I started the recording. Okay, chapter 7 for AP. Well, for AP, a chapter is a chapter is a chapter. We do the chapter, you take the test. We do the chapter, you take the test. For dual credit, this chapter is going to be a little funky. So if you want to make a note on the front of your notes on what I'm about to tell you, be ready. Like I said, AP, you can just kind of ignore this part because, yeah, doesn't apply to you. For dual credit, pages 1 through the top of 16, the very top of 16, that's test 2, potential test 2 material.
That's a lot of potential.
Some of the stuff won't be on there, but you'll see that when I send the review out this week, probably this weekend. Okay.
It's
Then,
on Tuesday?
test is on Friday.
Oh, like next Friday?
Next Friday.
Oh, bad, okay.
But this chapter is kind of weird because it's split. We end the material for dual credit on Monday for the test 2, but we can't stop, take a test, and then keep going with the chapter. So y'all's test is getting put to the 16th, which I mean it's always been there technically, but scheduling wise I had to push it so we can finish the chapter before you test. Which means page 17, where it says section 7.6, starts your test 3 material. So section 7.6 is the start of the test 3 material. Yeah.
7.6?
Yeah. That's on page 17. So if you notice, the geometric distributions won't even be tested for dual credit. So test 2 is through the top of 16. Test 3 starts at 7.6. So if you almost wanted to, you could rip this packet in two if you're one that you categorize like a notebook or something. Okay. That's, yes.
Real quick, so like, wait, never mind. You said next Friday, remember that?
Yep. Which,
Hopefully we'll have a home game that day.
y'all do have a home game the 16th.
Yes, sir.
That's the first home game. Which kind of stinks to have a test on that day.
It's all good.
Okay, chapter 7. So, chapter 6 looked at probability. Chapter 7 is going to look at random variables and probability distributions. So, we're taking probability and kicking it up a notch.
Woo.
We're going to start looking at graphs and tables and all that good stuff. It won't be fun, this probability.
So it's going to be like the probability chapters?
It'll involve probability. It'll be kind of like a blend of the probability chapter and chapter 4.
Okay.
Like we're taking chapter 4, chapter 6, putting them together, and then out comes chapter 7.
All right.
Okay, so first, we're going to start off, if my clicker will work. Come on. 7.1, looking at just random variables. What's a random variable? So a random variable is a variable whose value depends on the outcome of a chance experiment. A numerical variable. and it associates a numerical value with each outcome. This chance experiment could be something like me going around and asking you, how many dogs do you have? I don't know how many you have. I don't know if you're going to tell me 0 or 50. It's all chance as far as I'm concerned. There's 2 types of random variables. We talked about this in chapter 1. Discrete and continuous. So, does anyone remember what a discrete variable, numerical variable, does?
That was where it's like a 1, 2, 3 type deal, right? Where it's like a specific numbers.
That's right. And then, Will, what's a continuous random variable?
The number is like not finite. Basically like it goes on and on pretty much.
That's right. That's exactly right.
So like a number line would be continuous, right?
Yes, to an extent. I mean,
Like just like the fact, like that's one line, it covers everybody.
yeah. So examples of random variables might be a grocery store manager looking at how many broken eggs he has in a carton. Or an environmental scientist might want to find out the amount of ozone in an air sample. Since these values change and they're subject to some uncertainty, these are random variables. The grocery store manager can't go pick up a carton of eggs and say, without opening it, this carton has 3 broken eggs in it. How would he know that? He hasn't seen the eggs. So there's some chance in there. Okay, so we already talked about it, but just as a review, if you don't remember it, maybe you want to draw these number lines beside discrete and continuous, or write something beside it, because it's for sure on the dual credit homework that I gave you all today. Discrete is a set of possible values that's a collection of isolated points along a number line. Typically, it's a count of something. So it's just individual points. Continuous is the set of possible values that includes an entire interval on a number line. This is typically a measure of something. So time, what did we say earlier? Ozone, the amount of ozone in the air. We're measuring something. So it could be a range of numbers. Okay, so here's what we're going to do. These next 8 questions, there's 7 on the front, 1 on the next page. I'm going to, just based on where you're sitting, kind of break you into groups. Riley, I want you to join Julissa and Stephen for this activity.
Sounds good.
Y'all 4 can be like a little group, and then AP, y'all can be a group. So I'm going to give each group 2 or 3 problems to look at, and I'm going to give y'all about 2 to 3 minutes to talk about them, see if they're discrete or continuous.
Okay.
So the first group, Riley, Julissa, and Stephen, I want y'all to look at numbers 1, 5, and 8.
Another thing, all right.
1, 5, and 8. Okay. Justine, Isaiah, Tara, right? Tyra. I messed up someone's name third period. I'm like, y'all just bring these rotten eggs I'm talking about from the carton and just throw them at me. Because it's week 7 and I still don't have y'all's names done. I want y'all to work number 2 and 6. So number 2 has 2 parts to it, so that's why I'm only giving y'all 2. 2 has 2 parts. So 2 and 6. AP, y'all are going to do 3, 4, and 7. And y'all can talk about them. We just need to figure out if they're discrete or continuous. That means like if you roll a 3 and a 4, you're just gonna look at the 3.
If you said you don't have a choice, you want to do
Where? Oh, no, that's actually just the.
Oh.
Yeah.
And y'all found number 8 on the next page.
Yeah.
That doesn't seem fair.
Do you remember the email that you used?
I tried both of the emails I usually use.
Do you try your school?
I tried both.
Oh, I know what you're using. Last name, first name, middle name, all caps, that's the word.
Let me try the thing I forget how. Because I think we all do that. Did we do our lunch number?
I didn't.
Okay, y'all still need more time? Are y'all ready? Y'all good? Okay. So number 1, Riley's group.
Alright, I got it.
Fair die is rolled, and then you look at the number on the up face.
I'll say it's discrete, because you can only get one of like 6 numbers.
That's right, it's discrete. So even if your group didn't answer it, you may want to write these down as we go, if you didn't do them already. Number 2, a pair of dice are rolled. The first variable we're going to look at on number 2 is the sum of the up faces. So Brandon's group. What did y'all say that one was? That's discrete. What about the next one? The smaller of the up faces. That one's also discrete. We're still talking about a pair of dice. Yeah. Okay, AP number 3. A coin is tossed until the first head turns up. Discrete? That's right. Okay, group 4, or number 4, I should say. I think that goes back to y'all's group, right? Riley? It's it's still y'all. That's right. So, choose and inspect the number of parts, and you want the number of defective parts. Discrete. Good. Okay. Now y'all go to 5.
We put continuous.
That's right, because you're measuring the voltage. Yep. Okay. Shataro's group. You observe the amount of time it takes a bank teller to serve a customer. Time is continuous, yes. Number 7. Measure the time until the next customer arrives at a customer service window. That's continuous. And then the trickiest one, perhaps, is number 8. Let's see how y'all did on this one. Okay, so we're going to inspect randomly chosen circuit boards. If the circuit's defective, we assign it a 1. If it's not defective, we assign it a 0. What kind of variable is this?
I put discrete just because it looks to me like you can only have a 1 or a 0.
Yeah. Yeah, it's discrete. And then one way you could do this, so you add up how many 1s you got, and that gives you the number of defective boards.
I think I didn't even go with that.
So it's still a counts, or discrete.
Because the way I saw it was like it was just saying like he's inspecting it and not it's working. So like that, like that's all I read it. He wasn't like trying to say like oh it's working but or anything like that. It's just like either it works or it's not.
Yeah. Yeah. Okay, so that's all 7.1 dealt with. Was just naming types of variables.
All right.
And dual credit on that assignment that I passed out, that's just like that. You just have to say discrete or continuous. 7.2. We're going to look at discrete distributions and, yeah, just probability distributions for discrete random variables. So a probability distribution is a model that describes the long-run behavior of a variable. So it's not just a, okay, I'm going to roll a dice, oh, probability is 1/6. I mean, it could be that, but that's, again, based on long-run observations. So we have a fictional place called Wolf City, and the regulations prohibit no more than 5 dogs or cats per house. So just to hear y'all's opinion, does that sound like a lot or not much? That's a lot?
I have like 7 cats, so.
Yeah, That, to me, that's not much. I grew up, we had at one point 13 horses, 2 commercial heifers,
Farm boy.
3 dogs, and about 20 cats.
I see why you're an egg.
But with all those 20 cats, we never had snake or rat problems. So, what's funny though is my parents, probably in the next 5 to 10 years, are going to sell out. And the neighborhood they bought property in, for when they sell out, only allows 2 animals. It's like, okay, Mom, you gotta pick. Which animals are you taking? She's like, well, I'm getting rid of the horses. And we don't have the heifers anymore. I'm getting rid of the horses. I said, okay.
I have a horse and a cat.
Well, they have like a third of an acre on the lake, so there's not going to be room for a horse. Anyways, let's let X be the number of dogs and cats in a randomly selected household in Wolf City. Is this variable discrete or continuous?
Discrete.
It's definitely discrete. What are our possible values for X?
1, 2, 3, 4, 5.
Those are most of the values, yes.
0.
0.
I didn't really got there.
I went from having all those animals, and then when I moved off to go to college, went down to 0 and haven't gotten one yet.
I have a pet.
I don't have a pet.
You got a stray cat. That always helps.
Yeah. Mainly because the apartments I live in, or I have lived in, whether in college or here, the dog breeds I would want, they were strict. So it's like, well, heck, why get one?
You like big dogs?
I do. I grew up with all big dogs, and so
Get a Saint Bernard.
I'm looking at, when I get one, I either want a German Shepherd
Pitbull.
or an Australian Shepherd. Those are the 2 I'm kind of looking at. Maybe a lab, but I don't know. Labs can go either way. They can be either really protective or they can be pushovers. Anyways, so we have our possible variables. Well, the Department of Animal Control has collected data over the course of several years, and they've estimated the long-run probabilities for the values of X. So those are our probabilities. Probability that you have 0 dogs or cats is 0.26, 1 is 0.31, and so on.
Oh, according to like the people who have been there before?
Yeah.
Gotcha.
What do you notice about the sum of all these probabilities?
Yeah.
It equals 1. That's right. Yep. So this is called a discrete probability distribution. We can also display it in a histogram with the probability on the vertical axis. So if we look at this histogram, oh, go back. Oh, actually, I'm getting ahead of myself. I'm not even going to say because what I was about to say is wrong. Yes.
Is this discrete?
This is discrete, yes. So here we have each possible value. Let's see, where is it? There it is. Each possible value for x, and then their probabilities. So it's almost like a relative frequency histogram. Not quite. So let's talk about just discrete probability distributions in general. So they give the probabilities associated with each possible value of x. And each probability is the long run relative frequency of occurrence. So we're not doing this over like 10 trials. Ask 10 people, okay, this is the probability. This is happening over a long time period with a lot of trials. And it can usually be displayed in a table, or it usually is displayed in a table, but it can be displayed with a histogram or even a formula. And these steps are blank, so if you didn't catch that, those are your blanks at the bottom of page 2. So let's look at 2 properties of discrete probability distributions. So please I'm writing it down. Okay. So for every possible value of x, the probability has to be between 0 and 1 inclusive. We can't have anything smaller than 0. We can't have anything bigger than 1. It can include 0 and 1, but it can't be smaller or bigger. And then for all values of x, just like we saw on that first example, all the probabilities must add to equal 1. If they don't, it's a bad distribution. It's not valid. So that's one way you can check to see if it's valid. Do they all add to 1? And then are they all between 0 and 1? If it doesn't meet both of those, then no, it's not a good distribution. Okay, so back to our dogs and cats example. I'm going to actually work these with y'all. I'm going to work these 3 with y'all, and then for the next example, we're going to go back into our groups again. Just to keep things interesting. Okay, so they give us the distribution, and they just ask for different things here. So first one, what's the probability that a randomly selected household in Wolf City has at most 2 pets? At most 2 pets. What are our possible values here if we're at most 2? 0, 1, or 2. second. Okay, so we're going to write this in symbols because I want to point, I'll end up pointing something out. So probability that X is at most 2 would be less than or equal to 2. So let's look at the ones we actually want. We want 0, 1, or 2. So just this group of values. How can I get the overall probabilities then? Just add them up. So 0.26 plus 0.31 plus 0.21. What would that give you?
Pretty straightforward.
What's that? That's right. What were you saying, Riley?
Pretty straightforward.
This part it pretty much is.
Alright.
Today at least will be straightforward.
I'm all good with that.
Okay, next one. They ask the probability that we have less than 2 pets. What values would that include?
0 and 1.
0 and 1. So we just want 0 and 1. Now, I'm going to write this as X, like the problem says, less than 2. So strictly less than 2. What probabilities would I add together? 0.26 and 0.31. And what would that get you? 0.57. Yeah. And then the last one. They want more than 1, but no more than 4. So what possible values could I have here?
2, 3, 4.
2, 3, and 4. So when we put this into symbols, we're going to say the probability that X is bigger than 1, but less than or equal to 4. So what values would I add up in this case? That's right. 0.21 plus 0.13 plus 0.06, which altogether gets you 0.4. I'm going to just put the 0 at the end since they've all been, everything we've done has been the 2 decimal places today. Okay, now throughout this process, notice the attention that I paid to my signs here. Less than or equal to, strictly less than, strictly less than or equal to. So let's make a note here that for discrete probability distributions, This note's a little bit long, but I'm writing it just like y'all are. For discrete probability distributions, you must pay close attention to the signs. Or I'll say the signs. Really, it should be to whether certain values are included. If they're included, those would be the inequalities that say less than or equal to, or greater than or equal to. Or not included. That's where it's less than, just strictly less than or strictly greater than. And again, this is for discrete probability distributions. We're going to see at the end of the day where when we get to continuous, the signs don't really matter much. Okay, next example, I'm breaking y'all back up into your groups. Justine's group, I want y'all to do that first question. So the at least 3 items. AP, I want y'all to do between 2 and 4. So that last question, Riley, Julissa, and Steven, I want y'all to do the one that says at most 3 items. So they're all in that salesman example.
Okay.
Y'all have the second question, y'all have the first question, AP's the third question. So Yes.
Medical for the doctor.
Okay, let's look at it. So, for the first group, they want the probability that he sells at least 3 items. So, how did y'all set that one up? Uh-huh. Let me do that. Probability that x is greater than or equal to 3. Uh-huh.
Let's talk about a little bit.
That's right. That's exactly right. Okay, next group. Are y'all next? You listen? Or was it AP? Y'all. Okay. So how did y'all set this one up?
Okay, so in the parentheses, we put X is less than. Okay, 3. And then we put, 0.2 plus 0.35 plus 0.15 plus 0.12. And then we got the equals, 0.82.
That's exactly right. And then the third one. AP, it's y'all's time to shine.
The probability, that 2 is less than or equal to X, is less than or equal to 4.
Uh-huh.
Is equal to 0.15 plus 0.12 plus 0.1.
Yep.
Equals 27.
That's exactly right. Perfect. Y'all knocked that example out of the park. Quick little side story for y'all. You ever want to get a salesman to quit calling you back? Stay on the phone with them for 30 to 40 minutes. I can't remember if I told this class the story or not. My dad had this salesman that kept calling him every single week. He's like, hello? He's like, do you in construction? I am. Well, let me tell you about these new tools that I have. I think they would really benefit your company. Thanks, but I'm not interested. Oh, okay, have a good day. Next week comes around. Calls my dad again, her number. So they're doing that like spoofing type deal where they pick someone else's number to call you from. He answers, same thing. I'm not interested. I think, oh, you sure? Yes, I'm sure. I'm not interested. They hang up on him. Third time, he calls them, or they call him. And he had just gotten in his truck and had like a 30 to 40 minute drive ahead of him. So he's like, oh, really? Tell me about these tools. And so the guy spent probably 10 minutes talking about this new tool. And he's like, not really interested in that one, but last week you mentioned you had this tool. Tell me more about that one. So the guy spent about another 10 minutes telling him all the bells and whistles on this new tool. Now that you've described it much, I don't really think that I'm interested in that one. This is the line of work I'm in. And so he told me, like, I install septic systems. What tools do you have that can help me with that? Oh, I think you need this new type of, I don't even remember what the tool was. So he spends another 10 minutes describing this tool to me. And my dad said, look, in case you haven't gotten the hint, I've told y'all 3 weeks in a row to quit calling me. I'm not interested. I am not interested in any of y'all's tools. I never have been. Please quit calling me. But sir, can't we convince you to buy something? We've just spent 40 minutes talking to you. We need to make a sale. He said, no, I'm not interested. Quit calling me. Take my name off your list. They cussed him out and then hung the phone up. But never called him back. Yes.
Do salesmen even exist anymore at this point?
Yes, they do.
Oh.
Yep, they do. They'll do like that guy did, cold call you as a telemarketer trying to sell you something. And if you go to like a dealership, before you get out of your car, usually there's a salesman right at your door. Oh, you here to buy a new car? And so it's, yeah, there's still salesmen out there.
I hate we got any questions like that.
Okay, where's my pen? There it is. Okay, that's the next one. So I need to go back to the PowerPoint. Let's see, we've done the dogs and cats. We've done the salesman. Okay, so this isn't in your notes, but just to kind of jumpstart us into the talking about continuous. So a probability histogram has its vertical scale adjusted in a manner that makes the area of each bar equal to the probability that the event occurs. So that, where this really plays into everything is when we look at continuous random variables, which we're about to look at next. We're getting into it today. It won't be on the homework today, but we still need to cover it so we can get through everything tomorrow. On average, I need to average 4 pages of notes this week per day. We're actually going to get almost 5 pages done today. But yeah, tomorrow's examples are long. Bring your calculator tomorrow before I forget. If you don't have it, bring it tomorrow. Okay, so a probability distribution for a continuous random variable x is specified by a mathematical function, f of x, and it's called the density function. So the graph of a density function is a smooth curve called the density curve. The probability that x falls in any particular interval under the curve is the part that's under the curve but above the x-axis. So we can't go negative here. Now, let me ask you this, just to kind of set up one of our examples we're going to do here in a second. If something is continuous, like let's say we're measuring distance, what would be what do y'all think the probability would be? Let's say I'm doing distance that you drive per day. What would the probability be that you drive 10.58761 miles?
Pretty low.
Being that specific, it'd be pretty darn close to zero, right?
Mm-hmm.
So when we look at continuous distributions, we're not looking at certain values, because getting that specific, there's pretty much a next to nothing chance of that occurring. We're actually going to see where that probability for a certain value is zero, because we're on the continuous range. We're interested in a range of values, not one specific point. Okay, so let's look at the properties of continuous distributions. The first one is that f of x has to be greater than or equal to 0. We cannot have the curve go below the x-axis.
Greater than or equal to, or greater than?
Greater than or equal to.
Gotcha.
It can be 0, but it can't be less than 0. Did y'all catch that blank on the top of the page, or did I talk through it?
Area under the density curve?
Yep.
Yeah.
Okay. Second one is the total area under the curve equals 1. So those of y'all that are in AP Stats, have y'all had AP Calculus yet? You have? So
Integral?
yeah. We're not going to talk about integrals. We're not going to use them, but that's essentially what we're doing here. Yep. Okay, so let's consider the random variable x, where x is the weight in pounds of a full-term newborn child. So would this variable be discrete or continuous? Continuous. It's a measurement. So let's suppose we report the weight to the nearest pound, and then we do a histogram. So the histogram's not right below it, but maybe you want to draw an arrow down to that first histogram, from suppose down to that first histogram. Because that's the one that it's talking about. That would be our histogram. So the area of our rectangle that's centered over the 7 represents the probability that x is between 6.5 and 7.5. But now, that doesn't look bad, but let's see if we can make it smoother. So now suppose that we report weights to the nearest tenth of a pound. Oh, I guess let me back up. I forgot a question here. If I add up all these rectangles, what should my sum be? 1. The area would always be 1. So if I added them all up, the area would be 1. That still holds true even when we get the weights reported to the nearest tenth of a pound. Notice we went from almost like stair steps to now it's looking more like an actual graph. The bars are so small. You can still see the jaggedness, and then on your paper it almost looks like the picture is pixelated. It's not pixelated, those are all little bitty rectangles. And then, so notice we have a smoother curve. I already mentioned all that. Starting to have a smoother appearance. If we smooth it completely out, this would be our resulting histogram. So if we measure it with greater and greater accuracy, the histogram approaches a smooth curve. This shading here represents the probability that our weight is between 6 and 8. This last one is an example of a density curve. That's a density curve. Okay, last example of the day. It's another 3-part example, but still it's the last one.
Like for notes, or are we moving on after that?
Well, after we do this next 3-part example, we're done.
Oh, bad.
If you look on page 5 and it says application processing, we're gonna stop right before that example. Yep. So almost get through 7.3, but not quite. So let X denote the amount of gravel sold in tons during a randomly selected week at a particular sales facility. Suppose the density curve has a height f of x above the x value, where f of x is equal to 2 times 1 minus x, as long as we're between 0 and 1. If we're not between 0 and 1, it's 0. So that means our density curve looks like that. Essentially, it's just a line. Any place else, it would be 0. Again, remember, this is not saying the probability of getting 0 is 2. That's not what this is saying. Don't read it like that. This is not a histogram. This is a density curve. You haven't? Piecewise functions? Yeah. That's what, when I saw it preparing, I'm like, good memories. Piecewise functions. In the area under curves. I could really, this sounds mean. This is going to sound really mean. But I'm like, I could really mess them up if I threw calculus in here.
Nah.
No, I'm not going to do that.
Integrals aren't that hard. I guess the Riemann sums.
Yeah. Riemann sums are pretty bad.
They look scary, that's it.
Integrals aren't bad if you know derivatives. If you don't know derivatives, then integrals are like, what the heck is going on here?
That is true.
Okay, so let's look at our first workout problem on the top of page 5. Since it's a workout problem, I'm doing it with you. This one? No? That one. Okay, what's the probability that at most half a ton of gravel is sold during a randomly selected week? So what we want to do here is find the area under the curve as long as x is at most. So less than or equal to 1/2. Yeah, I know some of y'all that are in dual credit that are ECHS have not had geometry. Just bear with me here. Hopefully you'll remember some of area from, I think it was 8th grade.
I thought you took geometry sophomore year.
It's different. Some do, some take it junior year, some take it senior year. If you're ECHS, right now they have it senior year.
For what, senior year?
For early college high school, yep.
That's great.
Okay, so what we're wanting to find is the area up until where x is 1/2. So this area right here. So I'm going to just kind of put that in words. That way maybe y'all write it, and then when you're studying your notes, you'll know what this is. So the probability would be the shaded area under the curve and above the 0 to 0.5 interval. On the x-axis. Okay, what shape does that make? A trapezoid, right? So if we find the area of that trapezoid, then we have our probability. So I'm not even gonna, I'll write it up here. So we're gonna do 1/2 the area, or the area of the trapezoid is 1/2 plus base 1/2 times base 1 plus base 2 times our height. The bases of a trapezoid are the two parallel sides. So how long is one of the bases?
2.
2. How long is the other base?
1.
1. So our bases here are that one and that one. What's our height? What's this distance?
0.5.
0.5. Or we could also say 1/2. Either way works. So what would the probability be here then?
Mm-hmm.
3/4, that's right. So the probability that x is less than or equal to 1/2 equals 3/4. Yes. Questions on this example?
So did we do more of this? Like, what are these things that do multiple of those?
When we get to normal curves, there could be, yeah. No, I want to start using calculus in here. Sorry. Because I really would like to say, oh, this is the integral from 0 to 5 to 0 of 2 times x minus 1 dx. But then only two of us probably would know what that means.
Yeah.
Can't do that, sorry.
It's way faster.
Yeah. Okay. Next one. What's the probability that exactly half a ton of gravel is sold during a randomly selected week? So we want exactly half a ton. So go to 1/2 up here. Okay. Now, let me ask you this. The probability here, if we put it into words, the probability, which remember is that x equals 1/2,
Is this zero?
it would be 0, yeah.
That would just be 1 over.
Yep. Probability would be the area under the curve and above 0.5. Now, can I, so that's this area right here, this line that I drew, that would be our probability. Can I find the area of a line? No. So this probability is 0. A line has no area.
So why didn't we show it in this one?
It's a line. It wants to know the probability that x is exactly 1/2.
Oh, okay.
So it's just this line that we're finding the probability of.
Oh, I should, okay, I got you.
So this was that kind of that foreshadowing that I was talking about. Can I drive exactly what's the probability I drive exactly 10.85976
Yeah.
miles? You look at me and be like, the probability you drive exactly that many is pretty close to 0. Same concept here. Except it's not pretty close, it is 0. We cannot find, if it's continuous, we cannot find the probability of a specific x value. Won't work. Okay, questions on this one? Okay, onwards to the last one. What's the probability that less than half a ton of gravel is sold? The probability that x is less than 1/2. Well, let's see. I don't want to equal 1/2. I want to be less than 1/2. I'm going to put a dotted line because I don't want to equal it. I can be anything less than that. So this whole area. What do we notice about this one? What do you think? So does the probability change when we find the area, whether we include the 1/2 or not? The probability that x is exactly 1/2 is 0, yeah. But since we can get infinitesimal, I can't even say the word I'm trying to say. Yes, that word. Close to 1/2, our area would not change. So this would be the same as the first problem. We would still find the area of our trapezoid.
Would you not put a less than sign instead of equals?
What's that?
Would you not put a less than sign instead of equals, or is that something else?
And about right here?
Yeah, like, you would put it less than whenever you get to the final product, or is that something else?
I think that's something else. So this one is still the same. And it's going to be 3/4 or 0.75, however you want to write it. So I'm going to pretty much write the answer to this question down here. No. This is different. Because if we were doing discrete, we would have said, yes, it's different. Yes, it changes. This is different from discrete probability. Where it does change. So where it does change the probability. So on continuous, inclusion or not does not change the overall probability. So we're going to stop there. We'll do that last example of 7.3 tomorrow. Any questions on today's stuff? Let me stop the recording right quick and then I'll head that one.